Hey everyone, how are you all doing? Tell me, how is your preparation going on? Well guys, I'm hoping that you all are doing great and you must be enjoying your preparations. So to help you out, we are here in the batch of excellence where we study your syllabus with respect to boards, JEE as well as NEET. And guys, myself Sagar Darvi, your chemistry teacher, and I welcome you back to this organic chemistry course where we are learning a chapter which is Aldehydes, Ketones, Carboxylic acid and acid derivative. So guys, in the previous class we got introduced to a chapter Aldehydes, Ketones and Carboxylic acid. We saw how structurally carbonyl compounds looks like, and because of their structural features, how their boiling point and solubilities varies with respect to other organic compounds. Then we also saw some methods of preparation of aldehydes and ketones. So in our today's class number 2, we will be continuing some more methods of preparation of aldehydes and ketones. So guys, let me show you first what exactly I will looking forward to learn in our today's class. So on your screen, you all can see we'll be talking about some methods of preparation of aldehydes and ketones, starting with by the distillation, dry distillation of calcium salt of carboxylic acid, or you can say dry heating of calcium salt of carboxylic acid. Followed by, we will also learn methods of preparation of aldehydes ketones using some reducing agents, and those reducing agents would be acting upon acid chlorides, nitriles and ester. Once that is done, then we'll be talking about methods of preparation of some aromatic aldehyde and include several reactions such as Etard reaction, where we will see how toluene can be converted to benzaldehyde. The same toluene can be converted to benzaldehyde using another set of reagent, that is action of CrO3 in acetic anhydride. Followed by, we'll see the commercial method of preparation of benzaldehyde is by side chain chlorination followed by hydrolysis. And finally, one more name reaction, that is Gattermann-Koch reaction for the formation of aromatic aldehyde, which is benzaldehyde. So dear students, are we all ready to go ahead? Yes? Super. So let us start with the first reaction, that is preparation of aldehydes and ketones from the calcium salt of carboxylic acid. So we're going to heat the salt of carboxylic acids, of course calcium salt of carboxylic acid, to prepare corresponding compounds. Just to understand that, let us say if we have if you look at this compound, this is calcium salt of formic acid. If I structurally represent it, it would look like this: H C double bond O O C A O C double bond O, and further connected to H, right everyone? You can certainly see that this part is a salt of or conjugate base of formic acid, so you can call it as formatines. So there are two formatines connected to calcium, as calcium being divalent to one calcium ion, that is Ca+2, and we need two formatines connected to it. So that's how the actual structure looks like, and which you can also simply write down like this: HCOO twice Ca. Now when we heat this, look. Now let's say this bond between calcium oxygen is breaking in favor of oxygen. So let's say this bond have been broken like this, making this carbon deficient. As soon as this bond shifts here, this calcium will become trivalent, and hence this sigma bond will break towards carbon. Now this carbon already has 4 bonds, so if this sigma bond delocalizes here, making valency of carbon 5, this hydrogen will come out in the form of H minus. So we are getting H minus, which will then attack at this deficient carbon atom. Now all these things are taking place simultaneously. Just see that one more time. Bond between carbon and oxygen have been broken towards oxygen, or you can say towards calcium metal, making this carbon deficient. So this is becoming like formylation ion. As soon as this bond shifts here, carbon becomes trivalent. So bond between calcium and oxygen breaks towards the carbon, which makes carbon pentavalent. So the sigma bond breaks towards H, converting that into hydride ion, which is then attacking at the deficient carbon of formylation ion. Which means you can say that this H attacking at this C double bond O, converting this compound into HC double bond OH, which is nothing but formaldehyde, HC double bond O, and this is the new H which has attacked, resulting in the formation of symmetrical aldehyde, which is formaldehyde. Right, everyone? In addition to that, we have got CaO and CO2. CaO and CO2 can be collectively written as CaCO3. So we've got a salt, CaCO3. So you can see here, when we take calcium salt of corresponding carboxylic acid, naturally in a calcium salt both the carboxylate ion which are attached has to be same, because if you allow CaOH twice to react with any of the carboxylic acid, since CaOH twice is a diacidic base which can donate 2 OH minus ion, if you treat such kind of acid with monobasic acid, one CaOH twice will always react with 2 equivalents of carboxylic acid, and that's why both these values of carboxylate ion will always going to be identical. Now if these two values are always identical, then the group attached to carbonyl carbon and the group attacking at the carbonyl carbon both are going to be identical, and that's the reason the aldehyde which we are getting is a symmetrical aldehyde. So we got formaldehyde by heating calcium salt of formic acid, which means you can say this is calcium formate. Similarly, now let's say we have got calcium salt of some carboxylic acid. You can call calcium carboxylate or calcium alkanoate. Structurally, we can also represent it this way. RC double bond O, RC double bond O, one more O. So that's a carboxylate ion. Let's take one more carboxylate ion, RC double bond O and O. Now this anions will be connected to calcium. So we have got calcium salt of carboxylic acid and we are heating it. Now see, one fact we already know, that this bond will break towards calcium, this will further break and CO2 will be released. Meaning in general, we can represent the breaking of a bond in this way. So what are we eliminating is CaCO3, calcium carbonate, and this R minus, R along with the bond pair, is going to attack at the deficient carbon of this carbonyl carbon. So the product obtained would be RC double bond O connected to R, RC double bond O, and CaCO3 is our byproduct. Well guys, having said earlier, in any calcium salt of carboxylic acid, these values, the values of alkyl group in both this part of molecule is going to be identical, because two equivalents of same carboxylic acid are going to react with one equivalent of CaOH twice, because CaOH twice is diacidic base. Hence, two values mentioned in the form of R are always going to be identical. That indicates that this ketone which is obtained is certainly symmetrical ketone. So guys, what we have learned here, calcium salt of carboxylic acid upon heating produces aldehydes or ketone having two identical values of those alkyl group. Like in case of aldehyde, it is going to be formaldehyde. In case of ketone, it is going to be some symmetrical ketone. So question arises, in order to prepare symmetrical aldehydes and symmetrical ketone, these methods are perfect. But what if we are aiming to prepare unsymmetrical aldehyde or unsymmetrical ketone? Can we use this method? And even if we use this method, is that method going to be efficient method for the preparation of those kind of unsymmetrical aldehydes or ketones? Let's have a look at that. So now let's assume we are willing to prepare unsymmetrical aldehydes. So let's say preparation of unsymmetrical aldehyde. Unsymmetrical aldehyde meaning we are talking about preparation of aldehyde other than formaldehyde. Okay. So see what we are doing. Let's say we took calcium salt of carboxylic acid other than formic acid. So other than formic acid meaning you're taking value of alkyl group as R, not H. So that is calcium carboxylate. Right? So we have calcium carboxylate. Now this calcium carboxylate is brought in contact with calcium formate. So calcium formate. Calcium formate. And carrying out dry heating. Well, everyone here? Now the way we did it earlier, imagine if I would have just had calcium salt of carboxylic acid upon heating, we would have eliminated calcium carboxylate. So one preferred, or you can say one probable product is where R minus attacking at the deficient carbonyl carbon of its own molecule, giving you symmetrical ketone again, R C double bond O R. Second possibility from the other side, that is from calcium formate, if you heat this, then reaction will result in the formation of, let's say we are eliminating calcium carbonate again, CaCO3, CaCO3. So just like it happened here, the hydride ion will attack at the deficient carbon of C double bond of formal group, so we'll be getting HC double bond H. Meaning one simple product is what we have seen earlier. We'll be getting symmetrical ketone and symmetrical aldehyde, that is formaldehyde. But other than that, because these two salts we have taken together and subjecting it to distillation, another possibility is that this R minus may attack at the deficient carbon of formylium ion to give you R C double bond OH, that is some other aldehyde other than formaldehyde, or similarly H minus can also attack at the deficient carbonyl carbon of some other acyl group, so we'll be getting R C double bond OH. Meaning if hydride ion of one of the calcium salt attacking at the carbonyl carbon of other, and same way with the first and second molecule that way as well, so we will be getting product as 2 equivalent of R C double bond OH. So that's our major product. Right everyone? R minus attacking here will be giving one molecule of RCHO, and H minus attacking here will be giving second molecule of RC double bond OH. And other than that, as we consider, we may also get formation of symmetrical ketone plus symmetrical aldehyde, which is formaldehyde. Right everyone? So the product obtained here is unsymmetrical aldehyde, unsymmetrical aldehyde. And as you can see, unsymmetrical aldehyde is obtained as a major product. And the rest two are going to be minor one. Hence always remember, whenever they give you only one type of calcium salt of carboxylic acid, you'll write down the symmetrical product only. Of course, with only one type of calcium salt of carboxylic acid, you'll only get the symmetrical aldehyde or ketone. But the moment they mention two different salts, then always remember, although you're going to get symmetrical aldehydes and ketones as a minor product, but if they have given us two different salts of carboxylic acids, which means they are expecting us to write down the mixed product. Mix as in this cross product, where two values of alkyl group are going to be different. So that point has to be kept in mind. Now everyone, similar to this, now let's say if we have got next example, let's say we have been given Okay, adipic acid. Adipic acid is a dicarboxylic acid having 6 carbon, right? You start with oxalic acid, 2 carbon, malonic acid, 3 carbon, succinic acid, 4 carbon. So OMSG, G for glutaric acid, then A for adipic acid. Total is going to be 6 carbon. So the fifth member of dicarboxylic acid has total 6 carbon. So let's say we have CH2, CH2, this is CH2, CH2, altogether 4 carbon, 1, 2, 3, 4, 5, and one more 6. Okay. COOH, and here as well I'm taking COOH. And let's say we are treating this with CaOH twice. And we are eliminating water here. So this is acid-base neutralization reaction. So see what we have got. This was adipic acid. Now adipic acid has lost its H plus ion. So this is going to be adipate connected to calcium. So just like you had calcium carboxylate, calcium formate, that's a calcium salt of adipic acid. So calcium adipate you can say. And we can represent it this way upon elimination of water. See, we have got how many CH2? 1, 2, 3, 4 CH2s. 2 C double bond OO and connected to calcium. Alright, calcium salt of adipic acid 1, 2, 3, 4, 5 and 6. Yes. And now let's say we are subjecting it to dry heating. Again, as we saw, we know the mechanism precisely. So you can say that this bond shifted here, this will shift here further, so that this bond will go back on this carbon, making it anionic, and this anionic carbon will now attacking at the deficient carbon. So effectively what we are removing, Ca, C, O1, O2, O3, CaCO3. So you have removed CaCO3. Anionic carbon is attacking here. So you'll be getting cyclic structure of how many carbon? 1, 2, 3, 4, 5. Cyclic structure of 5 carbon, which means straight away we can put it this way. This was your first carbon, let's say. So if you just number for understanding 1, 2, 3, 4 and 5, you see fifth carbon attacked at first. You'll be getting cyclic ketone of 5 carbons. So this product is nothing but cyclopentanone. Cyclopentanone. And of course, along with this, we've got byproduct CaCO3. Alright guys, so that was all about preparation of aldehydes and ketones by heating calcium salt of carboxylic acid. Depending upon the requirement, we may get symmetrical aldehydes or ketone, or we can also prepare unsymmetrical aldehydes or ketones, or even if we wish to prepare cyclic ketone, this is the way we can prepare it. So guys, proceeding further with the next reaction. Well, next method is called as Rosenmund reduction. Rosenmund reduction uses acid chloride and we pass a hydrogen gas using a special type of catalyst. I want you all to pay attention to this. Although reaction is very easy, mechanism is out of scope for us, but there's a wonderful chemistry behind this reaction. I want you all to pay attention. This as well as the next one. So what Rosenmund reduction says, acid chlorides are treated, or acid chlorides are allowed to react with passage of hydrogen gas in presence of a special type of catalyst, that is palladium metal coated or palladium metal deposited over barium sulfate. Sometime you will find in presence of sulfur or quinoline. in boiling xylene as the solvent. Xylene is basically dimethylbenzene, which is used as a solvent that converts this acid chloride into aldehyde. Okay. Well guys, firstly I want you to understand, imagine if I'm just passing hydrogen gas in presence of palladium metal only, and we are not using barium sulfate. So what will happen? We know the fact that palladium is an active metal which provides its surface area for hydrogen gas to get adsorbed on this. So concentration of hydrogen gas on that palladium metal surface increases a lot. And that's why excess of H2 gas will always be available to carry out reduction. Now for the time being, although this is not the mechanism I've told you, mechanism for this Rosenmund reduction is out of scope for us. So let us assume the H2 gas is used for reduction of this acid chloride, and just for the understanding, this is H2 and I'm breaking this bond. Ideally this is not how the mechanism takes place, but for the understanding we got HCl as a byproduct and RC double bond OH is what we have got. Now what I said, we are assuming hypothetically that the barium sulfate is not taken. So H2 gas will be getting adsorbed on the metal surface, that is palladium. Since palladium is an active metal, provide enough surface area for a large concentration of H2 gas to get adsorbed on the palladium. So higher the concentration of H2, after acid chloride being converted to aldehyde, even this carbonyl carbon can be reduced by that excess of H2, and then aldehyde will be reduced to primary alcohol. So in that case, we are not going to get our desired product, which is aldehyde. Hence, the provision is made in such a way that this palladium metal is taken with barium sulfate in presence of sulfur or quinoline with boiling xylene as a solvent, where the role of this barium sulfate is very, very important. This barium sulfate acts like a poisoning substance for the catalyst palladium. So barium sulfate is basically going to poison. So you can say a poisoning substance. What does that poisoning substance means? When palladium metal is coated over surface of barium sulfate, this barium sulfate reduces the surface area of palladium. Since barium sulfate reduces the surface area of palladium, it does not allow large concentration of hydrogen gas getting deposited on palladium. So the concentration of hydrogen gas have been deposited in lesser amount on palladium due to poisoning ability of barium sulfate. Poisoning meaning not letting more H2 gas getting adsorbed on palladium by reducing its surface area, because of which limited amount of H2 gas reduces this acyl chloride into aldehyde and over reduction is avoided. Once aldehyde is formed, since concentration of H2 is very less, this further reduction of carbonyl carbon does not take place and we get our desired product aldehyde. This whole catalyst, that is palladium coated over barium sulfate in presence of sulfur or quinoline along with boiling xylene as the solvent, is known as Lindlar's catalyst. The same catalyst, dear students, we have also studied where alkynes can be converted to alkenes. So the controlled reduction of alkyne to alkene can also be achieved by this Lindlar's catalyst. The same catalyst we are using here to reduce acid chloride to aldehyde, where the role of barium sulfate is to poison the metal catalyst. So barium sulfate is not the catalyst. Catalyst is still palladium, but its activity have been reduced, its activity have been decreased or poisoned such that the over reduction of aldehyde is avoided. Now I have been using term other than this, we also use sulfur or quinoline. The role of sulfur or quinoline is, in case if excess of H2 will be available, that sulfur will react with that excess of H2 and gets converted to H2S. That's how sulfur also plays an important role in helping the poisoning ability of barium sulfate. So guys, anytime if you find the question given where acid chloride is to be treated with the Lindlar's catalyst, that is palladium metal coated over barium sulfate in presence of sulfur or quinoline in boiling xylene, you simply have to stop your reaction up to aldehyde. No further reduction to be done. Just to give you example, let's say if we have got let's say they are saying we have got benzoic acid. That's benzoic acid. This benzoic acid is further treated with SOCl2. SOCl2 being chlorinating agent, and that chlorinates the hydroxyl group of either carboxylic acid or alcohol. This OH will be effectively substituted by chlorine, which in turn converts this benzoic acid into C double bond OCl. That is benzoyl chloride. And now let's say upon arrow they are saying you have to treat this with H2, PD, BaSO4. Now they further might not mention sulfur and boiling xylene, but the moment you see PDBSO4, it means palladium metal poisoned by barium sulfate. So you have to do control reduction only. So control reduction meaning you'll assume only one H2 will be added across C double bond O and Cl. Again, I'm reminding that is not the mechanism. Just for the sake of understanding, you'll break down this bond. Add H's on either side. So H will be added to this carbonyl carbon, and that would result in the formation of the product, which is benzaldehyde. Right everyone? Plus HCl. Now see what change has taken place. Carboxylic acid have been converted to aldehyde. Generally what we have seen so far in the chapter of alcohol is if you take an alcohol and treat them with mild oxidizing agent, they get converted to aldehyde. Those aldehyde upon further reaction or further oxidation get converted to carboxylic acid without any change in the number of carbon atom. So far it's very commonly we have seen that aldehyde have been converted to carboxylic acid, but this time what we are doing? We are doing a reverse process. Benzoic acid have been reduced to aldehyde. So this is one way by which carboxylic acid can be reduced to aldehyde. Alright everyone, so that reaction is what you call it as Rosenmund reduction. That way reaction is pretty simple. It's just that you guys need to understand the role of barium sulfate or sulfur in the palladium metal catalyst, and the name of this reagent, the name of this catalyst is a Lindlar's catalyst. Similar to this, yet another important reaction is Stephen's reaction. Just like Rosenmund is important, remember Stephen's reduction is equal importance. Stephen's reduction says nitriles, or you can say alkyl cyanides, are reduced with SnCl2 in HCl. Well, so if I talk about reaction of SnCl2 plus HCl, everyone see here. Let's say if we have got tin metal and treating that with HCl, I'm talking about only tin metal. If you observe here, tin is in zero oxidation state, right? That's a elemental state, a metallic state. Now when Sn react with HCl in excess, so Sn gets converted to SnCl2. 2 indicates that you need 2 chlorines, so let's say if you multiply by 2, so other than this 2 Cl, you are also left with 2 nascent hydrogens. That indicates tin metal upon reaction with HCl give you SnCl2 plus 2 nascent hydrogen. Let me tell you here, tin has been converted to +2 oxidation state, which is the stable oxidation state of tin. If this is the stable oxidation of tin, the reaction would always want to go in the forward direction and produce the nascent hydrogen atom irreversibly. Irreversibly meaning you are going to get the nascent hydrogen because the product obtained is more stable. So you get excess of such nascent hydrogen. Because you get excess of such nascent hydrogen, if I allow alkyl nitrile to react with tin in HCl, I'm not talking about SnCl2 in HCl. I'm assuming if I take tin in HCl, because tin reacting with HCl produces SnCl2 plus nascent hydrogen, and because in SnCl2 Sn is in stable oxidation state, more and more of tin and HCl will react with each other, and reaction will always proceed in the forward direction, producing more and more amount of nascent hydrogen. So if nascent hydrogens have been obtained in excess, then those nascent hydrogen will keep on adding across carbon-nitrogen triple bond. Imagine if if two nascent hydrogen added, you will be getting CH double bond NH. Then still there is double bond, add two more H's, you will be getting CH2 single bond NH2. Meaning, in case of this reagent, we will be getting our product, which is the complete reduced form of nitrile, that is primary amine, RCH2 NH2. But we aren't using tin metal plus HCl. What are we using? SnCl2 plus HCl. Okay. So if I'm using SnCl2 plus HCl, then what happens is here. In SnCl2 Sn, that is tin is in +2 oxidation state. Let us say this is being treated with HCl. Reaction reversibly gives you SnCl4 plus 2 nascent hydrogens. Well, SnCl2 with HCl produces SnCl4. That indicates here tin is in what oxidation state? +4 oxidation state. So you have got 4 Cl. Here I have got 2, and in the product if I have got 4, meaning I need 2 more HCl here. So 2 chlorine upon addition to the Cl2 gives you SnCl4, and 2 nascent hydrogen have been set free. Now if you compare these two tins in +2 state and +4 state, guys, when you study carbon family, carbon, silicon, germanium, tin and lead, as you come down the group, we have studied that lower oxidation state becomes more stable than the higher oxidation state due to inert pair effect. Of course, you guys have studied this in group 14. So according to inert pair effect, I'll just write it down. With respect to inert pair effect, if you compare the stability of tin +2 with tin in +4 oxidation state, +2 oxidation state is more stable than +4. Because +2 is more stable, as soon as SnCl2 upon HCl produces SnCl4 and 2H, it gives you reversible reaction, meaning nascent hydrogens are produced, but they are produced reversibly, of course, because +2 state is more stable. So this equilibrium will always lie in backward direction. If equilibrium is lying in the backward direction, meaning amount of nascent hydrogen produced is always going to be limited one. Because it is limited one, this nitrile cannot be completely reduced to amine, so it is reduced to an aldehyde. How? We are going to see that now. Alright. So just for the understanding, look at this, guys. Since conditions being acidic, let's say the lone pair of this nitrogen attacks at H+. So you will be getting RC triple bond NH+. Now this upon reaction with SnCl2 plus HCl, which produces 2 nascent hydrogens. Let's say this 2 nascent hydrogen added symmetrically across carbon-nitrogen triple bond. So we will be getting RCH double bond. Earlier was NH. Now you added one more S, so this will become NH2 plus. So this is what have been obtained. And if you carry out further hydrolysis of this, let's say if you separate this and carry out hydrolysis, you will see this will be converted to RC double bond OH. So the product obtained here is an aldehyde. Again, conclusion is nitriles have been converted to aldehyde by the action of SnCl2 and HCl. SnCl2 and HCl reversibly produces nascent hydrogen. Because the concentration of hydrogen produced in this reaction is very low, nitrile is not reduced to amine completely. It is being reduced to corresponding aldehyde. So guys, that's how we convert nitrile into aldehyde using Stephen's reduction, that is action of SnCl2 plus HCl followed by hydrolysis of the nitrile. Alright everyone. So let's say if the question is given like this. Well, so what they've given us is C2H6 subjected to monochlorination to give you product A. This product A is further treated with KCN, forming product B, and this product B is treated with SnCl2 in HCl, giving product C. What is your C is what we have to identify. So following the sequence of organic reactions one by one, ethane is given upon monochlorination. Well, so if we have got ethane, you can see in ethane all the 6 hydrogen atoms are primary and they are equivalent as well. So if you are carrying out monochlorination here, you can assume one of the hydrogen have been substituted by chlorine. That would result in the formation of monochloroethane, meaning CH3, CH2 and Cl. Right everyone? So we got ethyl chloride. Now we are treating that ethyl chloride with KCN. So KCN is a stronger nucleophile since it is capable of producing an ambident nucleophile, that is Cn-. Having studied in haloalkanes and haloarenes, now this ambident nucleophile can attack at this deficient carbon either by carbon as a nucleophile or nitrogen as a nucleophile. But more stable product is when carbon attacks as a nucleophile at the carbon. So basically ethyl chloride will be converted to ethyl cyanide, which you can also call it as propionitrile, which is this. Precisely I'm mentioning the triple bond also. Once you get this, and now if you see SnCl2 plus HCl, so that was your A, converted to B. Now B is allowed to react with SnCl2 plus HCl, meaning now they're talking about Stephen's reaction or Stephen's reduction, you can say. So SnCl2 in HCl will reduce this cyanide to aldehyde without any change in the number of carbon atom, because we can see the carbon of nitrile was still intact in aldehyde. So straight away, I'm not doing the entire mechanism again. CH3, CH2 have been converted to aldehyde. So the product that they asked us, C, is nothing but propione aldehyde. So guys, that is application of this Stephen's reduction. So far we prepared an aldehyde by 3 processes. Number 1, by distillation or the dry distillation of calcium salt of carboxylic acid. We saw how do we get symmetrical aldehydes on ketones, and if we need unsymmetrical, how to get that. Second method was conversion of acyl halides, acyl chlorides to be precise, into aldehyde using a Lindlar's catalyst and the reaction known as Rosenmund's reduction. We know how important is the role of barium sulfate or sometimes sulfur in it. And just now we saw Stephen's reduction. We studied the importance of Sn in +2 and +4 state using inert pair effect, how Sn +2 is more stable, because of which reaction of HCl with SSCN2 will always be reversible, giving you lesser concentration of nascent hydrogen. Hence it avoids the reduction of nitrile into amine, and that's how you get aldehydes. So guys, let's go ahead. Next is quite a simple reaction, that is converting acid chlorides into ketone using dialkyl cadmium. Well, as of now, I would suggest you guys to remember it in a simple way that look, if you look at this dialkyl cadmium, the value of R, let's say, is R minus since it is connected to metal. So R minus being nucleophilic, it will always attack the carbonyl carbon. This bond will break to make it O minus. O minus delocalizes back to push Cl minus. So basically one alkyl group from dialkyl cadmium is going to substitute this chloride ion from here. So if I've got 2 such alkyl group in dialkyl cadmium, you will need 2 such chlorine, so you multiply it here by 2. In short, this 2 R dash will replace this 2 chlorine. That's why you can see 2 R C double bond O R dash, and the 2 chloride ion which came out from acid chloride will combine with cadmium to give you cadmium chloride. As simple as that. This is just a simple reaction I want you to remember. And the simple mechanism is only what you are seeing on your screen. Okay, guys. So acid chloride upon reaction with dialkyl cadmium produces ketone plus cadmium chloride. So we are going ahead. The next important sets of reaction. Now listen to me carefully. We are going to use some reducing agent which are uncommon reducing agent. Probably you haven't heard of them earlier, but we are going to see them here. And as far as we can understand its mechanism, we'll try to understand it. But those mechanisms are going to be always out of scope for you. Previous year JEE also has asked question once on one of these reagents. Okay. So let us first learn how acid chlorides can be converted to aldehyde using hydride donor reagent. Remember, acid chlorides, nitriles and ester are the three compounds which can be reduced to aldehyde using some typical hydride donor reagents. One of that is LT-TBAL-H. It is an abbreviation. LT-TBAL-H stand for, let me first write down that. LT-TBAL-H stand for lithium tri tert butoxide aluminium hydride. So as you can see, basically the name is also suggesting that it is hydride donor. I repeat, LT-TBAL-H stand for lithium tri-tert butoxide aluminium hydride. Lithium tri-tert butoxide aluminium hydride. If I structurally try to write it down, forget about lithium, forget about tri. Tert butoxide. Look at that. Tert butoxide, how many? 3. Okay, let's say if I'm taking tert butoxide. Tert butoxide, we have been studying this since reaction mechanism where tert butoxide is used as a very strong base, right? So let's say this is tert butoxide. How many tert butoxide? Tri. So let's say I've taken them thrice. So tri-tert butoxide connected to aluminium carrying hydride. So valency for aluminium is 3. So 3 valency of aluminium were earlier fulfilled by this tert butoxide. You got extra hydride, meaning charge on Al will be minus. So this is tri-tert butoxide aluminium hydride whose charge is minus. So that is balanced by Li plus. That's how it became lithium tri-tert butoxide aluminium hydride, which is basically a hydride donor. Alright guys, now this reagent is used to convert acid chloride into corresponding aldehyde. So you allow acid chloride to react with lithium tri-tert butoxide and then you carry out hydrolysis to give you corresponding products. So just to make you understand the reaction, let me show you that reaction first. Let's say okay, let's say we have got nitrile. We have got acid chloride. And acid chloride is allowed to react with the first reagent here is LT-TBAL-H followed by hydrolysis. That will convert this acid chloride into aldehyde and no further reduction will take place. Okay everyone, now let's see how exactly is this conversion being carried out. Mechanism is out of scope for you, but I'm just explaining it to you for your understanding, that's it. So mechanism suggests we have got acid chloride, so R C double bond O, where O carries 2 lone pairs, so it is electron rich, carrying chlorine, which is a good leaving group as well. and this is brought in contact with Li, tritert butoxide. So AlH, and tritert butoxide I'm writing like this. TBU. Okay, let's right, everyone. Okay, let me correct it. Correct as in, let me just put the correct bracket here. Yes, now this is perfect. Now see what happens. Li plus and this is Al minus. So oxygen lone pair will be donated to Li. So we'll get bond formation between O and Li, which result in the formation of RC double bond O, one lone pair intact, one have been donated to Li. So we'll be getting OLi like this, carrying chlorine. Or you can represent this Li bond like this. And we have got ALH O C CH3 thrice, and this whole present 3 times. Now look, since O has got positive charge, this bond will break towards oxygen, making carbon deficient. So Al, that is Al minus, will always lose its hydride here. So H minus is attacking at the carbonyl carbon. So what we are going to get is R. See this chlorine I'm putting down here. This is the new hydride which has attacked. Oxygen now has got 2 lone pair and connected to Li. Right, everyone? But you can see here, in addition to that, aluminum has now become neutral because it has lost this hydride. So Al bonded to O CCH3 thrice, and this is thrice further. Right, now see, this lone pair delocalizes back since chlorine is a good leaving group. So chlorine is leaving. Okay, now when chlorine is leaving, oxygen will be carrying positive charge here. So we will be getting R C H double bond O, one lone pair intact, but charge will be positive since one lone pair has delocalized, carrying Li. And whatever is your further reagent, Al O C CH3 thrice. Right? And now if you further subject it to hydrolysis, our second condition. So this Li will now come out as a hydrolysis, which will combine with the Cl minus which left to give you LiCl. And if this bond breaks here, your final product is going to be RC double bond O and H. So that's how you can see acid chloride using LT-TBALH have been converted to aldehyde. So this is your bulkier group, which is basically you can say weak or less concentration of hydride donor. So this is a hydride donor, but the concentration of hydride donated to the deficient carbon atom is always going to be in lesser concentration. So one molecule at a time produces one hydride donor only. So what I want you to remember, if you have acid chloride and ever if they mention LT-TBALH, convert that only to aldehyde. No further reduction will take place. So your product is going to stay only up to aldehyde. No further reduction to alcohol will takes place. So that's how we convert nitrile acid chloride to aldehyde using LT-TBALH. Now, other than this, like I said, esters and cyanide can also be converted by yet another hydride donor reducing agent called as deballage. Like we had LT deballage, this is deballage. What deballage stand for is, look here, deballage stand for diisobutyl aluminium hydride. Diisobutyl aluminium hydride, we call it as deballage. So when we try and draw the structure of this, we have got isobutyl aluminium hydride. How many isobutyl? 2. So let me first draw isobutyl. All right. Diisobutyl aluminium hydride. Okay. Yes, that's isobutyl. Let's see, we have got twice of this. So diisobutyl connected to aluminium and hydride. So that's diisobutyl aluminium hydride. You call it as deballage. All right. Now we can see here aluminium as of now has been in its normal valency of 3. It has got 2 isobutyl group and 1 hydride. So valency is 3, meaning in its vacant orbital it can still accept one more electron rich species and Al can become Al minus. Just like how AlCl3 can become AlCl4 minus. Likewise. So when you allow an ester to react with such deballage in hexane as a solvent at a very low temperature, so generally you will see deballage reduces ester at a very low temperature where ester group will be converted to an aldehyde without any other attack at any unsaturation if exists in an ester. Meaning in this alkyl group, if I have got some unsaturation, that is not going to get reduced. Only ester will be converted to aldehyde. How it happens? Let's see that as well. Suppose we have an ester and treating with deballage. Diisobutyl, so twice. Guys, hold on. I think we made a silly mistake here. We have written isopropyl. We want isobutyl. Okay. Isobutyl, guys. I'm just doing small correction here. Isobutyl. So this is CH2, CH3 twice. Yeah, this is isobutyl. Guys, small correction to be done here. We considered isopropyl earlier. This is isobutyl. So same way here as well. CH2, CH, and then we have got 2-methyl. Diisobutyl, right? And now see, this oxygen will donate its electron parent to vacant orbital of aluminium. So aluminium will acquire a negative charge, O will acquire positive charge. So if I draw that, it would be RC double bond O. Now only one lone pair intact, other donated to aluminium. So O shared electron will carry positive charge, aluminium gains, so will acquire negative charge, carrying one hydride. And down here we have got OR dash. This is further connected to CH2, CH, CH3 twice, This whole present 2 more times, right? Now what happens? In order to neutralize positive charge, let's say this bond shifts here. So aluminum, which is anionic, will donate its entire hydride group, which being nucleophilic will attack at the deficient carbon. So see, attack of hydride took place. So we will get RC single bond O now with 2 lone pair bonded to Al. Now aluminum have been neutralized because it has lost hydride. Here we have got OR dash and this new hydride which attacked, and aluminum in turn further connected to CH2 CH3 twice. Alright everyone, now eventually what happens? This lone pair will delocalize, OR dash will leave, being good leaving group. So we'll be getting RC double bond OH and the further group. So we have RCH double bond O, but now one lone pair have been delocalized, so charge will be plus, which is in turn connected to Al CH2 CH3 twice, right? And this whole present twice. Now if you carry out hydrolysis of this, that is the second condition, hydrolysis. This hydrolysis will be used to break down bond here, and you'll be getting your desired product, aldehyde. So guys, that's how ester can be reduced to aldehyde. Remember, no further reduction will be done. So in one of the previous year JEE, you will see the question was asked, some ester was given and deballage, and one of the option was aldehyde. There was one more which was alcohol, which was further confusing. Will aldehyde be further reduced by deballage? No, your product will only remain till aldehyde. Also, even if there is unsaturation in this group, which will not be further reduced. For example, let's say if we have got some unsaturated molecule like R CH double bond CH single bond CH2 and CO OR dash. Okay, so we can see we have got an ester and some alkyl group has got some unsaturation over here, and upon arrow, if they mention that we have to reduce it by deballage followed by hydrolysis, the only part we have to pay attention is the reduction of this. So simply what you can remember, imagine you're breaking down this bond. This part will be lost as a leaving group, OR dash, which in water probably might convert into alcohol, R dash OH by accepting H plus. But this part is going to form C double bond OH. No change at the double bond will take place. Okay, second condition was hydrolysis. The product will be R. See, I'm keeping double bond intact, so unsaturation hasn't changed at all. Unsaturation hasn't changed at all. Further, CH2 C double bond O H and whatever is your byproduct. So this you have to keep intact here. So guys, that was all about reduction of esters into aldehyde. No further reduction takes place. Just like ester are reduced to aldehyde using deballage, similarly even nitriles can be reduced to aldehyde using deballage. So simply you can remember the reaction, nitriles using deballage followed by hydrolysis will be converted to aldehyde. Now yet again, just have a look at the mechanism. Let's say we have got RC triple bond N. We know the fact N carries lone pair. We have got deballage, that is aluminium carrying hydride and 2 isobutyl group, so CH2. Alright guys, isobutyl sometime you might see written like this, IBU twice, that is diisobutyl. Okay, so here aluminum will accept lone pair from nitrogen, hence will become anionic, So you can write it like this. RC triple bond N formed bond with Al carrying hydride. Isobutyl group present twice. Now, aluminum has gained electron from nitrogen, so will acquire negative charge. N will become positive charge. Here, in order to neutralize positive charge, let's say if this bond shifts here, carbon is becoming deficient. So this entire hydride will now attack at the carbon. So that's the hydride transfer we will be getting. RC. This is the hydride which got attacked here. Double bond N, which will be carrying lone pair. And now we have got AlIBu twice. Now, if you further hydrolyze it, bond between carbon and nitrogen will be broken using water, and the C double bond will be converted to the C double bond N will be converted to C double bond O. The further steps is something really not an area of interest for us to look for. So we will directly say that this will be hydrolyzed. See, in fact, I have told you right in the beginning, you don't need to know the mechanism. You just need to know that nitriles can be reduced to aldehyde using deballage. So if you hydrolyze it further, we will be getting the product as RCH, and this double bond will be attached to O. So aldehydes have been obtained from nitrile using again deballage. So guys, we studied three substrates getting converted to aldehyde: acid chlorides, esters, and nitriles. And for this conversion to take place, we use two types of hydride donor. First one was LT deballage. LT deballage is used only in case of acid chloride converted to aldehydes. And then esters and nitriles can be reduced to aldehyde using deballage. In which important thing, in case of an ester, if there is some unsaturation present, it is not going to get reduced. So only the ester part will be reduced to aldehyde, and no further reduction will also take place. Alright everyone. So that was about some conversion of halides, esters, and nitrile into aldehyde. And now the next part we are going to talk about is how do we prepare aromatic aldehydes. So preparation of aromatic aldehyde, you will see two of the reaction where toluene will be converted to benzaldehyde. Well guys, again, reaction for this mechanisms for these reactions are not known. So we are just going to apply some of the simple tricks to be able to remember the reactions. Okay. Well, I want you to go through this reaction first. Okay, everyone here. So conversion of toluene into benzaldehyde using chromyl chloride in CS2 is what you call it as Etard reaction. Just a name reaction. Sometimes they might give you some reactants and ask you that this reactants is going to give you benzaldehyde as a product. What is the name of reaction? So toluene plus CrO2 Cl2 chromyl chloride in CS2 converting benzaldehyde is Etard reaction. Like I said, mechanism for this reaction is not known, so we'll try to remember some way so that we can remember the reaction in the easiest manner. Look, what we do here is, everyone here, we have got toluene. Let's say this is the toluene. At this carbon, 1 out of 2H, let's say 1H I'm writing here. Okay. And out of CrO2, 1 O, everyone, one of the O I'm writing between these two benzylic carbons. So I wrote oxygen. So before I write remaining 2H's, I have put oxygen. Okay. Which is further connected to Cr. Now see the H which I have removed from this benzylic carbon, add to another oxygen. Out of 2 oxygen, 1 you took here, Remaining one oxygen you combine with H, so you'll be getting OH. And other than that, what is left is Cl2. This is just for the sake of understanding. Same you do it here as well. O, Cr, OH, Cl2. I repeat what I did here. We know that benzylic carbons are always vulnerable for oxidation as well. So what I did, I kept one H intact. And remaining two H's, I oxidized it. So I wrote O first. So out of two O, one O each, I wrote it here. Okay. And now the H which you wrote, the H which was supposed to be at the benzylic carbon, those H I'm adding to another oxygen which is left here. So you got CrOH and remaining 2Cl, I put it here. Now let's say this is some unstable intermediate which is then subjected to hydrolysis. As of now, let's say you have taken water in excess, so 2H2. This 2H2 will help you to break down the bond here. So you're writing H, OH. Same way here, H plus, OH minus here. So your byproduct will be CrOH twice Cl2. And the main product will be, at benzylic carbon you have got OH and OH. So at benzylic carbon you will be having two OHs. So at benzylic carbon we have two OHs. So CH and two OHs. So two OHs at the same carbon also makes compound highly unstable, and such unstable compound immediately undergoes elimination of water. So let's say from here, I am eliminating a water. So this sigma bond between O and H, let's say, delocalizes between C and O. So see, what are we getting? C double bond O H. So we have benzene, C, H, double bond O. That's how we converted toluene into benzaldehyde. Again guys, this is not the mechanism, this is just a way to remember the reaction. So action of chromyl chloride in CH2 on toluene, converting that into benzaldehyde, is what you call it as Etard reaction. Also you'll have question only on the conversion basis for such kind of reaction, no mechanism would be asked. Like this, you can see toluene can also be converted to benzaldehyde using chromic oxide in acetic anhydride. So that is second conversion where I'm taking that here. Toluene, acetic anhydride in presence of chromic oxide at a lower temperature will also convert that into benzaldehyde. Now again, trick to remember the reaction is simply, okay, I'm taking the toluene again here. So CH2, I'm highlighting one of the H to the left here. Remaining two H's I'm writing like this. Plus this acetic anhydride, I'm writing here like this. O C double bond O CH3 C double bond O CH3. Guys, this is just a way to remember, okay? And you're carrying out reaction in presence of CrO3. Guys, we know the fact that CrO3, this CrO3 is oxidizing agent, isn't it? Yes, we know that this is oxidant. If this is oxidant, which means this is capable of carrying out oxidation of benzylic carbon hydrogen bond. So let's say this benzylic carbon hydrogen bond is going to undergo oxidation. So out of three, let's say two H's are going to get oxidized, which means I'm going to add oxygen between carbon hydrogen bonds. So COH, and oxidation here as well will also give you COH. At the same time, for the understanding, imagine from this two benzylic hydrogen you are eliminating a water. Okay, so two things happening. For remembering the reaction, you are going to oxidize CH bond, meaning imagine you are going to bring oxygen here and here as well between C and H, and those two H will be then lost along with this O. So what will be left for us is pi alternate pi, and now here we have got C H. Now see, these two bonds were oxidized, so we'll be getting O here. Like I said, these are going to get oxidized, and these two H's are lost. So after that O, it will be directly connected to what? COCH3. COCH3. And down here as well, COCH3. And then carry out hydrolysis. So if you carry out hydrolysis, for the understanding, hold on. So H and OH, H plus. On the other side where bond have been broken, OH minus. Likewise H plus and OH minus. You can see your byproduct will be CH3COH, CH3COH. Two CH3COH have been removed, and the carbon will be carrying two OHs. Again, two OHs at the same carbon will be unstable. So now we will have COH and OH. So two OHs at the same carbon is unstable. Being unstable, it will eliminate water molecule. So the sigma bond will shift back here to give you C double bond O. Hence we will say our product is pi alternate pi and CH double bond O, which is nothing but benzaldehyde. So guys, toluene can be converted to benzaldehyde by action of chromic oxide in presence of acetic anhydride at a lower temperature. So far aromatic aldehydes can be obtained by two processes. Etard reaction, you will take toluene, treat that with chromyl chloride in CS2 to give you benzaldehyde. And second, you can use chromic oxide in presence of acetic anhydride at a lower temperature. Toluene will be converted to benzaldehyde. Now just like that, commercially we also prepare benzaldehyde by side chain halogenation of toluene. So that's toluene, and we are treating that with chlorine in presence of HNu. Well, the moment we say we are carrying out reaction in presence of HNu, that clearly indicates that HNu will carry out homolytic fission. So this is going to be a free radical reaction mechanism. If you see Cl2 in presence of AlCl3, that indicates chlorine will be converted to Cl plus, that is chloronium ion. Chloronium ion being electrophilic, it will be the benzene rings ortho and para position which will be attacking at that Cl plus ion, right? That is called as ring substitution reactions. But when you see chlorine in UV light will carry out homolytic fission of chlorine-chlorine bond to produce free radical, and free radical will always attack at that carbon where free radical is stable. So free radical is always stable at benzylic carbon due to pi in conjugation with odd electron. So if now chlorination is taking place at the side chain which is present on the benzene ring, then you'll call it as side chain halogenation. So two types of reaction will compete with each other depending upon what reagent we are using. We shouldn't be saying competing, but of course whatever reagent you are using, accordingly the product will be obtained. If you see Cl2 in AlCl3, you will carry out substitution on the ring, that is ring substitution at ortho and para. But Cl2 in UV light will straight away give you free radical, and free radical substitution will always takes place at the benzylic carbon. So let's say we have got two Cl2 here. Since we are carrying out side chain substitution, we'll be getting pi alternate pi alternate pi, and at this carbon we have one H and two of the H's will be substituted by chlorine. So 2H substituted by 2 chlorine, so I'm writing 2 HCl. So 2 chlorine have been taken out, remaining 2 out of this 4 will be substituted here. Now this will be further hydrolyzed. So let's say I'm treating this with NaOH, aqueous, So 2NaOH will carry out nucleophilic substitution. Having studied in reaction mechanism, benzyl halide always undergoes nucleophilic substitution via SN2 as well as SN1. So both this chlorine being at benzylic carbon will be substituted by OH. So we will be getting a carbon with one H and two OHs. Again, two OHs at the same carbon makes compound highly unstable. So this is unstable diol, which will eliminate water molecule immediately. So the sigma bond will shift back. And you see we are getting our desired product. So at the carbon we have got H, double bond O plus elimination of water. And that's how the product obtained is benzaldehyde. Alright everyone, so that was third method for preparation of aromatic aldehyde, that is toluene. Upon side chain chlorination gives you can say at benzylic carbon 2 H is substituted by 2 chlorine. So this is nothing but 1,1-dichloro 1-phenyl methane ideally. So phenyl will be considered as a substituent on the methane carbon, and then upon hydrolysis will give you diol, which will eliminate water to give you benzaldehyde. And now one such final reaction, which is the name reaction, we call it as Gattermann-Koch formylation. You can see we have got benzene, which is treated with carbon monoxide in presence of HCl with Lewis acid catalyst AlCl3 or CuCl that converts benzene into benzaldehyde. Well, this is also a very simple reaction. Just to understand this, let's say we have got HCl brought in contact with AlCl3. AlCl3 being Lewis acid will accept lone pair from chlorine. As soon as it accepts lone pair from chlorine, you will be getting HCl, now getting associated with AlCl3. Eventually this bond becomes permanent and Cl leaves as Cl minus. So Cl minus have been taken by AlCl3 to produce AlCl4 minus. Or you can write this as AlCl3 dot Cl minus. AlCl3 dot Cl minus, one and the same thing. But look at this H. H has lost this electron. So H has come out in the form of H plus. The H plus which is lost here will attack at carbon monoxide, because if you see the structure of carbon monoxide, it looks like this. This is how carbon monoxide exists in its major contributor or more stable structure. Now since we have got H plus here, this lone pair of carbon will attack at H plus. So the protonated form of carbon monoxide will be C triple bond O, one lone pair and positive charge. Now this molecule can exist in its resonating structure, where if you just break the pi bond towards oxygen, the resonating structure would be H, C, double bond O carrying two lone pair. But this carbon has lost this electron, so the charge will be plus. This is what you call it as formylium ion. Formyl groups cation, so formylium ion. So one thing is clear, that AlCl3 plus HCl followed by attack with carbon monoxide will produce an electrophile, that is formylium ion, and that electrophile will now be attacked by the benzene, because benzene shows their characteristics reaction called as electrophilic substitution. So the next set of reactions simply would be, okay, I'll start from here. So we have got benzene, which is treated with H, C triple bond O, a lone pair and positive charge. Now look, this pi bond will break, making this carbon electron rich, which will attack at this carbon. This carbon is deficient, as we can saw in one of the structures, so pi bond will break towards oxygen, which will result in the formation of pi alternate pi. This H is intact. This carbon has lost electrons, so this is deficient, which has now attacked at C. H I'm putting downward this time. Double bond O carrying two lone pairs. Right, now this structure can be further stabilized by resonance as pi in conjugation with vacant. Then further pi bond will be in conjugation with vacant orbital. So we are not writing those resonating structure. Once you get this molecule, which is arenium ion, this will now be attacked by the conjugate base. So I told you, AlCl4 we can write always as AlCl3 dot Cl minus. So the Cl minus will now carry out deprotonation. So H would be lost as H plus, sigma bond will shift here, and as a result of which we will be getting product as pi alternate pi. And see, this pi bond came back again to regain the aromaticity, and this is further connected to C double bond O H, which is nothing but benzaldehyde. So guys, that was all about Gattermann-Koch formylation. We call it formylation because let's assume we had one H here, and this H have been substituted by a formyl group, so we call it as formylation. So that is the fourth method by which we can prepare an aromatic aldehyde. The first one was Etard reaction, where toluene converted to benzaldehyde by reaction of chromyl chloride in presence of CH2 at a lower temperature. Second method, toluene converted to benzaldehyde using CrO3 in presence of acetic anhydride. Third was, in a toluene, the methyl group which acts like a side chain was chlorinated to give you dichloro product, which upon hydrolysis gives you corresponding benzaldehyde. And finally, Gattermann-Koch formylation uses benzene, and that is further treated with carbon monoxide in HCl in presence of Lewis acid catalyst such as AlCl3 or CuCl, that converts into finally benzaldehyde. So guys, with this we are done with methods of preparation of aldehydes and ketones. In the next lecture when we meet, we study properties or reactions of aldehydes and ketones, the most important part starting now onwards. So stay tuned and attend all the classes. I'll see you soon in the next class. Thank you so much everyone.